Hi everyone, this is Mr. Bozade, and I'm going to work us through the first problem on worksheet 10. First problem says that we got a 200 gram, 20 centimeter diameter plastic disc that's spun on an axle through its center by an electric motor. What torque must the motor apply to take the disc from 0 RPM to 1,800 RPM, which is about 188.5 radians per second, in 4 seconds? Let's draw a little diagram of the disc and label the diameter, which is given to be 0.2 meters, which means that we know that the radius of this disc is actually 0.1 meters. We'll start with our net torque equals I alpha equation. It's our new equation, and we know that if our goal is to find the torque of the motor, this is a good equation to start with. So we know that the only torque that's being applied to the motor is the torque, that's being applied to the disc is the torque of the motor. So that's going to equal I of this shape, and we see that this shape is a disc, so I of a disc times alpha. Looking back on our rotational inertia page, the previous page, we see that the rotational inertia of a disc is 1/2 mr squared. So we can substitute that in. We can say that torque of the motor is equal to 1/2 mr squared times alpha. Then we can look and see how many unknowns we have. We see our goal is to find torque of the motor, so we don't know that. We do know the mass of the disc. We do know the radius of the disc, but we don't know the rotational or the angular acceleration of the disc. So we have two unknowns and one equation. So we're going to have to look somewhere else to try and solve for one of these unknowns. Since our ultimate goal is to solve for torque of the motor, it makes sense to look somewhere else for the angular acceleration of the motor. And a great place to look is in rotational kinematics. So let's start by listing out our rotational kinematics variables, theta initial, theta final, omega initial, omega final, alpha, and t, and seeing what values we know. We can say that the initial angle of the disk is 0 radians. We can say that it starts from rest, so the initial omega is 0 radians per second, and we know that we want it to get up to 188.5 radians per second, and we want it to do that in 4 seconds. With these values, we can look at our kinematics equations, and we can see that the best equation to use to solve for alpha is to pick omega final equals omega initial plus alpha t. We can substitute in our variables that we know and solve for alpha, and the angular acceleration of this disk is 47.125 radians per second. So now we know alpha over here, so our only unknown is torque of the motor, and we can go ahead and solve for it. So we'll substitute the alpha in. We know that mass of the motor, or mass of the disc, is 0.2 kilograms. We know that the radius of the disc is 0.1 meters, and now we've got our alpha, our angular acceleration of 47.125 radians per second. And then we can solve for torque of the motor, and we find that the torque of the motor that makes this plastic disc accelerate at that rate must be 0.47 Newton meters. I think one of the most important things in this example was just being able to think about a different way to find alpha and applying rotational kinematics to find alpha so that we can plug it back in and eventually solve for our unknown torque. All right, hope that was helpful, and I will talk to you later. Bye.